Good afternoon, everybody. We're all just so delighted that there's so many people here. This is the most I've seen in the classroom this semester. So for those at home, because we're connected with Zoom, come on in. There's plenty of room. We're spaced around, and we can hold the designated capacity, I'm sure, for these classes. So thanks a lot. I'm Gary Oberts. I'm the developer of this class, and we'll moderate it along with Dave LaRue, who's going to be the presenter. Just a few announcements. Please quiet your phones and don't make too much racket talking among yourselves when we're trying to get through a presentation, out of respect for the neighbors and our speaker, please. Restrooms, if you haven't found them before, are out the door and up the hill, about a 1-minute walk up to the train station. And the first building you encounter will be the restroom area there. Dave said he's going to be willing to take questions as he goes here. That gets to be kind of a complicated process in here because we want to capture the question on the tape that we make because we're videotaping the class too. So we'll try to get to you with a speaker, but Dave, if they go fast and don't let us get there, can you just repeat it? And you see that flashing at you all the time. There's a little sign up here. So he's going to do that. If you're at home, just put the questions in the chat. And what we're going to do is just continually review them as we go through here, and then we'll bring them up when there's a chance to bring up a question from home if there are any that happen to come up. And finally, feedback forms. Lucy is going to post those in the chat for those of you who are at home to connect and do your evaluation or feedback for the class. And of course, in the classroom, please fill them out if you want to. This is going to be 2 classes. So if you want to wait for both classes, that's perfectly fine too. Also, the class is going to be videotaped. So it takes a while for it to get into the remote learning center, but it will be there eventually. So if you see some things that you want to study a little bit more, just go into that video when it's available and take a look at it. Okay, let's see. So before I introduce Dave, I just want to pay a quick little tribute to John Bush. Those of you who follow the geology curriculum here know that we lost John last February. He passed away, and I just wanted to acknowledge all the great work that he contributed over the years. I did 18 classes with him. It's hard to believe there was that many, but he was always there when we needed to have a geology presentation that was made. He had some ideas that he brought in that we actually followed as well. So he was here for over 15 years doing that kind of contribution in geology, as well as his first love, which is what his degrees were in, which was chemistry, but he also did a lot of other things. He did the origin of the Earth, which is interesting. Meteorology, scientific breakthroughs, energy, and just so much more. His contributions and his knowledge were just great. And I just wanted to acknowledge John before we moved on. So yeah, that sounds good. Big round of applause for John. So it's my pleasure to welcome back Dave LaRue. This is the second time, I think, only the second time, but after the first time, we had a lot of people say, when are you going to bring Dave back to do some presenting? Well, we after a short close down from the pandemic, we got Dave back into the classroom here, and we're so happy about that. His first class in 2019 was the amazing, incredible, unbelievable geologic history of Orange County in Southern California. That video, by the way, is available at the Remote Learning Center if you want to go in there and take a look at that. There's also a second course that I wanted to mention too. When Dave's going to do 4 individual classes, but it's in 2 courses. So the second course is the Earth's Major Extinctions. That's on November 19th and December 3rd, same time as this class right here. And we'll just have Dave back for 2 more times. Please note that those dates are not consecutive. So we're kind of avoiding the Thanksgiving period there. So keep aware of that. So Dave received his PhD in geology from Northwestern University in 1979. And according to his bio, he spent his BS years, no pun intended, at USC. I think for us, that is not such a pun, but we'll see. He also taught at Stanford University, University of Puerto Rico, and has given many presentations, including the one that he's going to do next semester on music, some of the chords, rock and roll and blues chords. And also was a geologist with Chevron and Exxon during his working years. He recently retired, but remains committed to teaching. I think he's a really foremost on his agenda of things to do is to teach some classes and get in contact with people and teach them about the geology of Southern California. So his broad knowledge in regional geology, not having been born here, I rely on people like Dave to fill me in on what the regional geology things are of this area. So I'm glad to have him. Special interest in stratigraphy, sedimentology, 3D modeling, geologic impacts on development, Caribbean geology, and we're going to get him back here to do that one of these days. Petroleum exploration and exploration, and just so much more that he's involved in. So without further ado, this is Dave LaRue. Join me in welcoming him, please. Like that. You get it anywhere close to your mouth.
All right, and then post this on my pants.
Yep, or in your pocket or.
All right. Oh, my pants don't fall out. So this would have been a better class in June, so you could have appreciated the beach over the summer. So I apologize. All right, you ready?
Ready.
All right. Let's see, page down. Oh no, it didn't work. Oh, here we go. Okay, goal of this class. When you go to the beach in the future, you will look with new eyes, ask yourself some questions about the beach, and perhaps appreciate its beauty, glory, and ever-changing nature even more. With this goal statement now completed, I promise never to use that font again. All right, what is a beach anyway? A beach is a pile of sediment that occurs on the seashore, on lakes, and on rivers. The science of beaches focuses mostly on oceanic beaches and lake beaches. When we see piles of sand along a river, we usually call them river bars. So this class really applies to beach and lakes, ocean and lake beaches. All right, so types of beaches. You can have sandy beaches, muddy beaches, cobble beaches, or non-existent beaches. And I'll tell you when each one of those types occur. If my machine will help me. There we go. Oh, God. All right, that way. Ah, there we go. What science is there about beaches anyway? Can we talk about the best corn dog on the beach? Which beach is the filthiest? Which sunscreen to use? Where are the topless beaches? How can I be a friend to sharks? And why is beach parking so bad? Oh, come on. Remember this ad from Charles Atlas? That big guy kicked sand on the beach, right? And so he did the Charles Atlas and he ended up went from that skinny guy to that muscular guy. That's all about the beach, let's face it. This is not beach science. All right, what is beach science? Why are shorelines different? Where does sand come from? Why are grains of the sand, grains of the beach, all the same sand? You got these giant beaches like at Huntington Beach, all the grains of sand are the same size. How did that happen? That's part of beach science. How do waves affect the character of beaches? And what types of sand patterns do we see in the beach and how do they form? I guess I could use this mouse thing. Yes, there is actually a science about beaches. You can do a PhD on beaches. I was going to do my PhD on beaches, but then I realized it was all partial differential equations. So the math was so complex, I decided to do something else. Okay, the practical side of beach science. Can I build my house on the beach? Hey, all the sand is disappearing from my beach. Would a jetty help? Will building a pier impact the nature of the beach? Can I build would you want to buy real estate on this condominium? Okay, this is beach science in action. Gee, look, there's waves here. There's no waves here. It's calm there. That's the place that I'm going to go swim, in that rip current. Okay, and then of course, can I land my aquatic vehicles on the beach? There is a lot of studies of beach science in World War II associated with the Normandy landing. All right, so here's our beach. This is Newport Beach, and it's lovely. All right, the shoreline in the scheme of things. The shoreline is the intersection of the land surface. Here's the surface of the land with the ocean or water surface, and this becomes the shoreline. So the intersection of any two planes is a line, and in this case, the intersection of the water level with the land level is the shoreline. Okay, there's two types of shorelines, basically. There's the depositional shoreline, which tends to have beaches, and then there's the erosional shoreline where the land's uplifting in areas of uplift where you have cliffs. So that the reason you have some places you have a sandy beach and a cliffed beach is one's uplifting, one's subsiding. And this is, by the way, Huntington Beach on your left and Little Corona, of course, on the right. You've all been to Little Corona, haven't you? All right, that's required for this class. All right, factors. Okay, if you just consider now depositional shorelines, not the uplifting ones, but the depositional ones, things that influence the nature of the depositional shorelines are how big are the waves? What are the waves like? How big are the tides? What are the tides like? And are there any major rivers around? So if you're in the Amazon, it doesn't really matter how much the waves are influencing you because you've got so much water pouring in because of the Amazon. So each one of these factors influence the nature of the shoreline. Okay, features of erosional shoreline. So these are things that you'd see in areas of uplift. You typically see a sea cliff. There it says sea, this is for the people online, sea cliff. You might see a headland, which is a little point sticking out in the water. A sea stack is simply an island offshore. There's a headland and coves. You see the little coves. And an uplifted marine terrace. What an uplifted marine terrace is an old shoreline that's been uplifted. So where it says uplifted marine terrace, that used to be where the water was, but the land lifted up through earthquakes and so forth. And now it's a flat area on top of the cliff. Does that make sense? So this is Little Corona del Mar, and we can see the marine terrace. Here's the flat area. So that used to be a shoreline right there, and that whole area got uplifted. So that's a marine terrace. There's a sea stack. There's the famous arch at Little Corona del Mar. This little point sticking out is the headland. Here's a little cove. Here's the wave-cut cliff. So these are all features of erosional shorelines we can see down at Little Corona del Mar. They also, in this diagram, it also mentioned blowholes. Blowholes are a little bit harder to find. There's some in Palos Verdes Peninsula I know about, but they're little areas where you're right by the water and there's a crack in the rocks and the water comes, the waves push the water in and it goes shooting up in the air like you see in this diagram right here in this picture. So that's called a blowhole. Okay, so that was an erosional shoreline where there's uplift going on. Depositional shorelines also have characteristics. So here's some of the characteristics of a depositional shoreline. You can get barrier islands, you can get bays, lagoons. A sand spit is this curved area here. See that? Sand spit. Here's a beach. Here's a tombolo. A tombolo connects an offshore stack to the land with a little beach. Okay, ready?
What's the difference between the lagoon and the bay?
Probably about the same. Good question, though. Oh, yeah. Repeat. No, please repeat the question. It says here, flashing at me. What's the difference between a lagoon and a bay? I have no idea. I think I would use them about interchangeably, but maybe I'm wrong. Okay, this is an example of a tombolo. Remember, this is the beach connecting to a little offshore stack. And this is Gough Island in South Laguna. So this is very close to us. The Pirates Tower, you know, guys know about the Pirates Tower in Laguna Beach? Have you all seen the Pirates Tower? Google it and you'll have to go visit it. It's a little tricky to get to, but it's interesting. Anyway, this is right down the beach, about a quarter mile from the Pirates Tower. It's an old building that looks like a Pirates Tower and very photographic. All right, so that's Tombolo, right? We happy with that? Okay, let's look at, here's Newport Beach. And again, I'll do this for the people online. So we have this, here's the back bay. Here's the bay here, the Newport Bay, not Newport Lagoon, but Newport Bay. And you have this big barrier island that goes along like here. And then you got the breach in it. So what one of these features is the Balboa Peninsula. This is the Balboa Peninsula. Which is it which one of these sand bodies is it? What's that? I would have guessed a sand spit as well, but it turns out that this thing here was dredged. So originally this was a baymouth bar that extended all the way across, and they had to dredge that out to make it actually an inlet for the boats. So originally, this is from Martha's Vineyard. These are baymouth bars, and this apparently is what the Balboa Peninsula looked like prior to dredging. All right, so in summary, Newport Beach, our near neighbor from Irvine, has both depositional, this is the depositional, and then erosional shorelines, right? All right, that was our first introduction to shorelines. Next discussion, our friend sand. All right. So first of all, we, as a geologist I do some what's called sedimentology, study of sediments, and I also do stratigraphy, which is studying layers of sediments. So in classification of sediment, we have to define it. So this is a table showing how you probably have never, why would you have to make a classification of sand? Well, here it is. But at any rate, this is how you tell a clay from a silt, from a sand, from medium sand, from fine sand, from coarse sand, from pebbles. All of these things are defined in this table. You didn't think it was necessary, but now you know, all right? So this is a classification of sediment. Now, sediment sounds a lot like sentiment, right? So of course, a lot of people make jokes about sediments, tying it with sediment. Yeah, and you've heard the jokes, you know, don't take it for granite, things like that. Well, this is the same sort of thing. So here's a paper that was written, lithovolcanic sandstones derived from oceanic crust in the Franciscan complex, sedimental memories of source rock geochemistry. Who would write, and this is from the journal Sedimentology, who would write such a dorky joke? Oh, it was me. See that? D.K. LaRue and one of my students, Maria Sampaio. All right, back to sand, our friend. There's two types of sand in the world grossly, generally. There's quartzose sand, which we really don't call quartz sand, we call it siliciclastic, but in this class, to be easier, we'll call it quartz sand. And then carbonate sand. Okay, those are the two major types of sand in the world. Carbonate sands consist of broken down pieces of corals and algae, calcareous algae, clam shells, mollusk shells. It's all organic material that's broken down into little sand-sized pieces. So the thing is you have to have a lot of life going on to form a carbonate sand. So carbonate sands are really only found away from big rivers because the rivers would flood, you know, the reefs and so forth, and they like the tropics. So this is where you see carbonate beaches in the world, and you can see they're mostly near the equator, plus or minus, and they're typically around the position of coral reefs. Okay, so we'll talk a little bit about carbonate beaches, but they're the other type of beach. So again, carbonate sand, the sand grains all consist of little pieces of once living things in general. So the spiny things are sea urchin spines. The things with little holes on them, those are coral fragments. There's little clam shells there, and so on and so forth. So these are all examples of life forms that have been comminuted into little pieces and now represent carbonate sand. There's another type of sand this is also carbonate sand. It's called an oolitic sand or an ooid sand. And this doesn't have anything to do with life. They're some sort of precipitation of seawater that's not really well known, but they kind of look like M&Ms. So they've got coatings on them. See the coatings on them? These are the coatings. So these are called ooids, and they are also a form of carbonate sand that occurs but you can see it in Florida and the Bahamas and places like that. All right, so the formation of carbonate beach sands involves the death of living things. So here you can see some coral heads and some, let's see, different brain corals and different types of encrusting corals here. And the death of these corals after they get broken down form the carbonate sands. So all that sand on the bottom is dead remnants of this coral here. And this is a calcareous algae named Halimeda. And it has a little calcareous structure inside of it that when it dies, it forms sand. And that's shown here. So all of the sand here is actually formed from those little green algal plates. So a carbonate sand is all from the death of living materials, and it's, being swept around as sand. Quartz sand or siliciclastic sands basically comes from the erosion of mountains. So here you can see some granitic rocks, probably up in the San Bernardino Mountains or something. And you can see it's all weathering. This is called spheroidal weathering, where it weathers into these balls. All the minerals in the granite are turning into clays, and the quartz grains and the feldspar grains and different minerals in it are just sort of becoming, they were once part of the granite, and now they're just falling down as grains of sand. Then what happens is that sand gets washed into rivers. The rivers flow down to the sea, and then you end up, this is the Santa Ana River. So this is Newport Beach here and Huntington Beach here. This is the Santa Ana River, and this is what's bringing sand down to Huntington Beach and Newport Beach. All right, it's those big rivers. All right, so the river transports the sediment until it reaches its final destination, the beach. Sediment comes from the weathering of the mountains. Where did all the pebbles and the coarse material end up? Well, they probably were too heavy to move down, so it was only the lighter sand grains that made it down. And then why is the beach only sand-sized material? And we'll talk about that. Right now, if you go down to the Santa Ana River, again, between Newport Beach and Huntington Beach, you look at the water and it's clear. There's no sand being transported. It's only when we have those giant storms, where you have big floods and everything. And this is what the Santa Ana River looks like during a flood. That's when all the sediment is transported in. So normally the Santa Ana River is just sort of an estuary where the water comes in and the water goes out. But it's only during these gigantic rainstorms that we have in the winter that it really pumps the sediment down and refeeds the beach. That's what feeds the beach, the sediment. Do cliffs make sand? Cliffs generally don't make very much sand. They mostly make pebbles, cobbles, and boulders. It's really the rivers that bring in the sand. All right, so two types of white beach. Now we're going to look at beach color, because we all want to see pretty things in nature. So these are two beautiful beaches. On the left is from Florida, and the right is from Hawaii. The one on the left is basically the mineral quartz. It's a quartz sand beach. And on the right, it's a beautiful white beach, but those are all carbonate grains. It's all little dead little, animals and plants and so on and so forth, coral fragments and so forth. They both look like beautiful white beaches, but they're fundamentally completely different. Pink sand beaches. Has anyone seen a pink sand beach before? Where'd you see the pink sand beach? Where? Bermuda is very famous for their pink sand beaches. The reason they're pink is because they have this dead animal in it, or dead, I don't know, it's not really an animal, it's foraminifera, whatever that is. It's this pink thing called a homotrema. It's an encrusting foraminifera, and that's what makes the pink sand, is those little fragments of homotrema. There's black sand beaches. This is from Palos Verdes Peninsula, just up an hour from us, where I grew up. And this is a black sand beach, and all that black sand are volcanic fragments. These cliffs here are basalt, and when the basalts weather and form these black sands, it makes a black sand beach. There's green sand beaches. Anybody seen a green sand beach before? They're a little bit rare. This one's from Hawaii, and they have the mineral olivine, which is a green mineral. For you gem collectors, gem quality olivine is, do you know its name? Peridot. Other beach colors, purple is Pfeiffer Beach in sort of central California, and that's from garnet. And here's a red beach from the iron content on Prince Edward Island. Okay, let's go back to our favorite Little Corona and say, well, we've got pebbles here. See all these clasts and boulders and so forth at the base of the cliff, but we also have sand. So where's the sand, pebbles, and boulders coming from? Well, the bigger clasts are probably coming from the erosion of the sea cliff, but notice there's a little stream coming down right there, and there's a little valley that feeds Little Corona del Mar. So these sands are probably being flushed down the valley onto Little Corona del Mar. All right, and maybe gets a little bit from Big Corona next door. All right, this next section is so exciting. We want you to breathe normally and concentrate on serenity. There's this, you need to say things like Serenity Now. Have you heard about this? Serenity Now is the 159th episode of the NBC sitcom Seinfeld. This is the 3rd episode of the 9th and final season. It aired in the US on October, blah, blah, blah. While driving with his arguing parents, Stephen Koren, a writer for the Seinfeld, was bewildered to hear his father shout "Serenity Now" at the top of his lungs as part of a rage-controlling exercise his doctor had told him about, and questioned whether or not the phrase was meant to be yelled. All right, so this is a Serenity Mountain. We're talking about pebbles now. This is pretty exciting stuff. Do we need defibrillators on this? Gary, are we okay? We got one. Okay. Okay. This is exciting stuff. All right. Pebble and cobble shape. Who is this? Thank you very much. We've spent inordinate amounts of time trying to understand the shape of pebbles. What does pebble shape mean? What are the types of pebble shapes? This looks like some fake onion or, parody of science, but this is really science being done. The way we analyze pebble shape is we use some sort of device like that shown, and we measure if you have a pebble, we measure the 3 orthogonal axes of the pebble, and we measure the length, and we call it like the A, B, and C as shown here. So the long axis is called the A, the B is the center axis, and C is the short axis. I've measured thousands of pebbles. Isn't that sad? All right. So once we actually measure the pebble, we can define their shapes. If all of the lengths are the same length, it's basically a cube or a sphere shape. See that? So if the C to B ratio is 1 and the A to B ratio, B to A ratio is 1, then you're ending up basically with the cube. Other shapes include a disc shape, which is called an oblate spheroid, but we'll call it pancake shaped. A prolate spheroid, which is a hot dog shape. And then another one, bladed, which is kind of like a 2x4 shape, which is kind of wide and it's sort of in between the disc and the rod. So those are the classification of pebble shapes, and they're real. And this is from a paper published in the scientific journal. So I'm not kidding you. All right. Now you're going to get confused because pebble shape and roundness are different. This diagram shows roundness, which is the absence of corners. And the other one on the left shows the pebble shape. So these are the shapes like spherical, disc-shaped, or pancake, and so forth. And so the thing is, you can have an angular sphere is very angular spherical shape is basically a cube, whereas a well-rounded spherical shape would be a sphere. Does that make sense? So both of these guys have the exact same A to B to C ratios, but one's round and one's a cube. And that's because we're not including the roundness in them. All right, so that's how we define pebble shape. Again, exciting stuff. Now you're probably thinking, he's just kidding around. But wait a second, you're gonna, at the end of this, you're gonna go, whoa. I promise you. Okay. All right. Okay, these are examples of actual papers written on pebble shape. I'm telling you, there's really a science of pebble shape. Pebble shape development on Tahiti. Downstream rounding of pebbles, a quantitative review. When you use quantitative, that means it's very scientific. Experimental abrasion of pebbles, a 6-part series. All right. There's a lot of knowledge about pebbles out there. Okay. Let's make this more interesting. Will the shape of pebbles be the same in rivers as on beaches? There's a question for you. So if I give you a pebble in my hand here, can you say, oh, that's probably a river pebble, or oh, that's from a beach? Is there any fundamental difference? Okay, we got a no here. So if you started with a pebble and a perfect cube and you stuck it in a river and it transported it for thousands of miles, what shape would it turn into? If you took that same cube and left it on the beach for 1,000 years, what shape would it turn into as it rolled back and forth in the swash zone? All right. And what's your name?
Frank.
Frank says they're going to be the same. All right. In general, if you're on the beach, you tend to see hot dog shapes and pancake shapes. The idea is that the beach is kind of like a big piece of sandpaper and the pebbles rolling back. So if they're rolling like a rolling pin, they tend to become more hot dog shaped. And if they're just like a cube, they're going to be sanded into a disc shaped. So it's thought that beach pebbles tend to be more hot dog shaped and pancake shaped. In a river, they tend to be more spherical and a little bit more angular because, again, on a beach, you got that nice big sandpapery beach surface. When the pebbles roll on it, it's like, you know, being honed with the sandpaper. So in this study, we say there is a difference between the beach and the rivers. All right. Everybody looking at the picture? Look at this picture. Do you see a fabric? Which way was the current flowing? Why do you think that? All right. Well, we'll talk about that in a minute. But we think that we can tell the current direction. Conclusion, beach pebbles tend to be more rounded in either disc or rod shape from rolling and sliding. River pebbles tend to be more angular and spherical from the studies that have been made. All right. Cooling. Okay, this is our cooling off period. I know this was really thrilling, and we'll now have a brief time to cool down. Okay, more on pebbles, orientation of pebbles. Here's a paper from 1963 in Geographiska Annaler. Okay, again, we want you to calm down. Don't get too excited. There's two major orientations. You can either, a pebble can end up on the beach in any orientation, but if it is oriented, it's either parallel to the flow, which is called from shearing. So the pebble's forced into parallelism with the flow, or it's rolling and it's perpendicular to the flow. And if you look in this picture here, you can see some of them are in this orientation, some are in this direction. This one, these seem to be more, it would be a rolling position. I don't really see any shearing position in this one. So anyway, pebbles do become oriented in flows. So I don't want to disappoint you. Avoid disappointment later. Abandon all hope now. I expect to be disappointed, and I was not disappointed. And then, of course, money. Don't we have any sugar around here? There's more disappointment. Imbricated pebbles. So if you look, all of those pebbles are tilted. See that? Okay. We can tell the current direction from that. Was the current in that direction or in that direction? How many in this direction? How many in this direction? How many don't want to participate at all? Yeah. Okay. The reason the current was in that direction, and everybody online, the current is going towards the left, is because if it was going in the opposite direction, the pebbles would flop over. The currents would just knock that pebble in the other direction. So this is putting your back into the flow as much as possible. So these are called imbricated pebbles, and they tell you the direction of flow. Now, this isn't very important when you go to a modern river, but we see these in rocks that are billion years old, and we use them to assess where the currents were going in rocks of, you know, a billion years or any age. And so we go back to this picture, and you were arguing for some sort of fabric, and these were imbricated pebbles here. And here you can see the river stepping down and telling us the flow is to the left, and that's what the imbrication tells us as well. All right, now this is the test. You've been in a test. Okay, you've learned a little something about pebble shaped, right? Y'all excited? Okay, are these river pebbles or beach pebbles? Okay. And why do you think the river? All right. And down here, you can see these are a little bit more angular. You don't think they're, yeah, those are not beach pebbles. Okay, yeah, there's a close-up of them. Pretty spherical shape, right? And then these are kind of angular, but again, certainly not hot dogs and discs. Well, here's the interesting thing about these rocks. These are on Mars. So they use knowledge, all those papers on shape development in Tahiti, Nui, and so forth, to argue. This is from the last three slides are from Mars, taken with the NASA Mars rover Curiosity. All right, so all of those dumb sounding studies of pebbles that we talked about previously were actually used in a study of to prove that there was river flow on Mars billions of years ago. Pretty amazing. All right, so what did we learn about Mars? And now you can see why some people study pebbles. All right, how are we doing? 40 minutes. Okay, yep.
I was just wondering that when you showed that picture, those pictures of the pebbles on
Go, Gary.
Can you all tell that Dave spends a lot of time in the sun?
when you were showing those photos of the pictures on the pebbles on Mars, could you then determine how long Mars has been without water running consistently, as opposed to the rocks and the pebbles from rivers and ocean?
No.
Okay.
So the question is what do the pebbles, the river pebbles on Mars, tell us about the history of river flow on Mars? And the answer is nothing. We need to date the rocks. So the idea would be is obviously as soon as those pebbles become rocks, there wasn't a river there anymore, but we need to know when that was. And until you've dated the rocks, you can't do that. But other people have, there's a whole Martian geology thing. And there are people there that are much, a billion times more knowledgeable than I, that could tell you all they have all sorts of interpretations, but that's not my specialty. But we'll talk about Mars in my next class as well, if you're interested. Okay, the movement of sand. All right. Again, sit back in your seat, breathe calmly. We're getting to the exciting stuff. We made it through pebbles, but this stuff, okay, here we go. Why is beach sand mostly the same grain size? That's the topic we're going to look at. And there's going to be math involved. Okay, everybody, here we go. Okay, now I want you to be a little creative and picture a great, big, enormous, humongous, huge pile of dirt, such as we show in this picture. And imagine it all gets swept by an enormous flood. It's all eroded by a flood. The flood moves the dirt. How does the dirt move? Does it all move at the same time? Does it all move at the same speed? What happens? We need to know this, people. This is important. All right. And here it says, here is a big pile of dirt. Isn't this exciting? All right. So how our big, enormous pile of dirt moves in the flood? There's, first of all, first of all, in that big pile of dirt, if anything is soluble, like if there's any salts in it, they're going to dissolve. So they could be moving in solution. All the muds and clays tend to move in suspension. They'll float in the flow. So the river's flowing and all the muds and clays are in suspension. And by the way, those things can last forever. If you ever see, when we have these giant storms that pump water out into the rivers, the beaches will remain muddy for days and weeks, because once the muds and silts are in suspension, it takes a long time for them to settle out and make the water clear again. All right. So anyway, we got solution of salts, suspension of clays and silts. Saltation is the bouncing of sand grains. So that sand grain sizes tend to bounce. And then bigger things like boulders, pebbles, cobbles tend to roll and bounce and slide. Okay. Now, the interesting thing is they're all moving at different speeds. The suspension and solution are moving as fast as the river. The saltations are kind of bouncing a little bit slower. And then the rolling and tumbling of the big blocks is even slower. Okay, so that naturally separates our big pile of dirt into different populations. The act of separating things into different populations is called sorting. So the fact that beaches are all the same grain size is as a function of sorting. And this is one way that sorting happens. Each size fraction moves at different speeds. There is even math involved that we won't do. Okay, so imagine a big pile of mud, sand, and gravel. This is a plot of grain size here. So silt and clay and sand and pebbles versus flow velocity. So if your flow is only 2 miles per hour, bigger things won't move at all. Okay, big boulder, 2 miles an hour, water's moving too much, nothing happens. Maybe some of the sand grains are like rolling a little bit. Maybe the silts are getting picked up, but not much. But if the speed of the flow is 22 miles per hour, then all your sands there's probably a lot of creep going on with the big boulders, and the sands are bouncing along, and there's a lot of stuff in permanent suspension. All right, so it's the speed at which the river is flowing really tells you what and how individual populations of sediment are moving. This is another famous curve that in geology classes we all have to master, called the Hjulström diagram, and it shows velocity on one side and then grain size here, and it says that to get into the motion field, your velocity has to be about 20 centimeters per second, about like this fast. And then only one type of sediment will move when the velocity is about 20 centimeters per second. What type of sediment is that, class? Fine sand. So if you look right up from here, it says fine sand. So fine sand is the easiest thing to move, okay? And as the velocity increases up to 100, now all of these things are moving. And then up to 1,000, everything would be moving. Now, again, remember that as the flow continues, some things will saltate, some will go into suspension, and some will roll and slide. All right, so the magic of sorting is it's nature's way of making beaches with uniform grain sizes. It's the grain size, the sand grain size on a beach is a function of what grains are available and how much energy there is. All right, let's go on. I'm going to skip that. Okay, an example of sorting. Here's an example of sorting. Waves break on the beach and they bring in sediment. So the coarsest sediment tends to be where the waves are breaking, because that's where the most energy is. Now the wind, like at Huntington Beach and at Newport Beach, blows on shore, and it's going to take this sand, but it can only pick up, because wind is not a very effective means of transporting things. Imagine a 10-mile-an-hour wind versus a 10-mile-an-hour current. you'd get knocked over by the current, but not by the wind. So the wind has a real problem moving the sand. So the sand on the top of the dunes at Huntington Beach might be actually finer than you'd see in the surf zone. So that's an example of sorting in nature. All right. Everybody calm. We made it through the hard part. Okay. Now this is when I was your age, geologically your age. So when I was a newbie to geology, I had no idea of the world of bed forms. And I see people stumble over bed forms all the time, and they have no appreciation for them, and they're very glorious. So bed forms are the motion of the wind and water will change the surface of the sand bodies to form things like ripples and other features, as we'll talk about. Okay, so what we're going to talk about is how currents mold the sand into different shapes, right? All right, so as you this was only discovered in about the mid 1970s, and it was shocking to everybody. If you have a pile of sand and it's underwater, and you increase the current progressively faster and faster and faster, you change the nature of the shape of the sediment underneath the water. So at first, if you have a body of sand and there's a slow current moving over it, nothing happens. As the current gets faster and faster, it forms these ripples. All right. So these ripples are a equilibrium bed form that forms from a certain flow velocity. As you increase the flow velocity greater, these ripples here, which are little things about this high, get replaced by sand dunes, what we call sand dunes. Now, one of the problems is everybody thinks of sand dunes as those enormous things in the desert. Well, it's very, very common, and I'll show you examples, to get sand dunes that are like this high in rivers and on the beaches. And in fact, all of you have experienced dunes on the beaches. Have you ever walked down a beach, on the flat part of the beach, and all of a sudden fell into a hole, and then walked up the other side and then fell into another hole as you go towards the breakers? Those are dunes that you're walking over. They're like this high or this high, and they're a little tricky to walk over as you're walking towards the breaking waves. Anyway, so as you increase the flow velocity, you go from no movement to this ripple field to a dune field, and then all the dunes get washed out and it's a flat bed. All right. Now and here's an example of dunes in a river. So these form by river flow. And by the way, you can see little tiny ripples on their backs as the flow subsided. So these larger dune forms formed in the river, and then the river level went down and then left us to be able to look at them. So those are called, those would be dune forms in a river. And why am I telling you this? Just to tell you what they look like. All right. So on this plot here, we have grain size on the horizontal direction going from really fine to, pebbles over here. And then here's the flow speed here. Now, what happens is to go from ripples to dunes to plain bed, ripples to dune to plain bed, that only occurs at one grain size. If you change the grain size and go to really fine grain size, you can't form dunes. So there's all these weird relationships of sand bed forms that nobody knew before that have now been well studied. And then if you go so you cannot form underwater sand dunes in fine sand. On the other hand, if you go to really coarse sand, you can't form ripples. You go from a lower plain bed to dunes to an upper plain bed. All right. So you cannot form underwater ripples in very coarse sands, plus there's a lower and upper plain bed that forms underwater. Now, this is another amazing fact. Ripples, no matter how deep the water is, the ripples will always be the same, little things about this high. Dunes are a function of the water depth. So there's even a relationship that's been published that says the height of the dune times 12 is the water depth. So it's weird that these things look very similar, yet one has no relation to water depth, and one is very strongly related to water depth. All right, so that was different types of bed forms that occur on the beach and near the beach. And we'll talk, the reason I'm introducing this is we'll talk about what happens on beaches in a while. Okay, sand on the beach or mud. Energy and grain size. Why is the beach all mud? So if we imagine here's a beach here and there's breakers here and a swash zone, where would you expect to see the coarsest sediment based on the idea that we've talked about? Where should we see the coarsest grains of sand? More specifically in the shore face, but the shore face is right, but probably under the breaker zone, that's where the currents are the strongest, right? And indeed, you're correct. Coarser sediments are typically found under the breaker zone, a little bit into the swash zone.
But if the breakers are stronger there, they would be chopping those babies up into fine pieces.
No. Once you're down to a quartz sand grain or a similar mineral, they are indestructible because you can bounce them against they don't really grind down much at all.
Then how did the finer sediments happen?
The finer sediments get transported by the rivers and they end up offshore because there's no wave energy to move them out. Okay, so if there is strong wave energy here, all the fine sediment would be washed away because of the wave energy. So it's the lack of energy out here that allows settling of the finer materials. And that what the question was, I can't remember the question, but hopefully I answered it. Because I have to repeat the question, otherwise they won't pay me.
Big bucks.
The big bucks, yeah. I don't get paid just when. All right, so let's talk about a tidal shoreline. So in the previous thing, we said if there's big waves breaking, the grain size is going to be a bit coarser. Let's talk about a tidal shoreline. Where are the currents going to be the strongest? What's that? At low tide. So in general, this is where all the currents are moving here. When you're coming up to high tide, it just kind of creeps up to high tide if there's no waves around, and then it kind of goes back to low tide. So most of the current is down here. So it turns out that the best place to get muddy shorelines is in a tidal environment. For example, in the Newport Bay, Balboa Island and Lido Island are all surrounded by sand, but as you go up into the Back Bay, everything's mud, right? You've all been to the Back Bay, right? That's also your homework, to walk the Back Bay. So again, Balboa Island, all sand, which should be sort of closer to the low tide area. And then at the extreme ends of the tidal cycle in the Back Bay, it's all mud because there's no energy to push the sand up there. Does that make sense? Okay, and then in a river influence shoreline, where would you see all the energy and where would the coarsest sediment be found? Where would you find the coarsest sediment? Where would all the energy be in a river? Well, basically, it's in the channel. So the idea is that if you're looking for sand here, it's going to be associated with the channel. As you get into the overbank areas, it's going to be a swamp without any sand at all. So what we're learning here is that the shorelines are very different when you're considering wave, tidal, or river influenced examples. The beaches are different because the distribution of energy is different. So if there's no energy, you're not going to see coarse sand, pebbles, and so forth. You're going to see muds. Grain size in the shoreline environment is largely a function of the distribution of energy plus the availability and character of the sediment. If there's no sediment around, you wouldn't have a beach either. All right, waves on beaches. I've been told with a handshake or hands.
Why don't we take a break?
All right.
10 minutes.
All right.
Give David a little break here. Are there any questions before we do break up? Anybody have anything?
No math questions.
You've wowed them, Dave. They don't have anything at all. So, yeah.
Next subject. And I hope you guys can hear me online. All right. Waves on beaches. Oh no. There we go. Wait. You're spoiling it. All right, no, God, up. All right, no, down. All right. So you're sitting on a beach and you ask, where do waves come from? Then you ask, why does this woman have her arm around me? I don't know her. All right, what is a wave? Most waves form when winds blowing across the water surface transmit their energy to the water. So we'll talk about what waves are.
Not the moon and gravitational.
No, that's the tides.
Oh,
Prepare to be impressed. No, I'm gonna tell you exactly how waves form, and you will go, whoa. All right. So waves are surficial. Notice that the wave energy, here's the particle motion is circular associated with waves. So you get pulled into the crest of the wave, and the crest pushes you, and then you get pulled into the crest of the next wave. So it's a circular motion of waves. All right. But that circular motion decreases with depth. So if you're out in the surf, you all know that if you dive under the water, there's much less turbulence than if you're up near the top, right? That's why we all dive when we see an enormous wave coming in. Okay. So back to the previous one, page up. Most waves form when winds blowing across the water surface transmit their energy to the water. So does that mean that a windy day will have waves, class? No. Bigger waves originate from hundreds or thousands of miles away. All right, so those big storms shown in red here are places where the wind speeds are very high, and those are whipping up waves that can move thousands of miles. So what forms waves? You need three things to form waves. You need wind speed, wind duration, and a thing called fetch. Okay. So the fetch is the length of the area that the wind is operating on. Okay, and this will all make total sense in a minute. So then you have the wind speed. Obviously, if it's really, really windy, you would expect it to make larger waves than if there's no wind at all. And then if the wind is just for a second versus, for 3 days, obviously the 3-day wind will make, bigger waves. So all that makes sense, right? Yeah. All right. So wave height versus fetch versus storm strength. So this is a plot here of wind speed here versus fetch length in nautical miles. So if you want to see giant waves, like 55-foot waves, you need to have a body of water that's like 600 miles across minimum. Okay, and you'd need hurricane force winds. Okay, if you have hurricane force winds and you're in a little tiny lake, you might see 6-foot waves. All right, because the lake isn't big enough, the fetch isn't big enough to make the big waves. Does that make sense now? So, and let's be more reasonable. So you have a 30-mile-an-hour wind on a lake that's 2 miles across, you might see 2-foot waves. All right, but if it's a 30-mile-an-hour wind and you're in a small sea that's 500 miles across, you might see 25-foot waves. All right, so that's the importance of fetch. Now to get waves, this is the famous place of Nazaré in Portugal, where they're now surfing 100-foot waves. Have you all seen the HBO special on it? Yeah. Garrett McNamara, who's riding waves like this. All right, and there's actually a guy riding this wave. It's a really lousy picture. I think he's about here. They're just little tiny specks, and it's one of the most horrifying. It's like climbing, the Sierras without any ropes or something. It's just horrifyingly scary. But anyway, that's another problem. So when you see big waves, think that they came from far away from a violent storm. Okay, here's a perfect example. This is the Great Lakes. So, and it's showing fetch length, which is basically the length of the lake. So the prevailing winds are shown with red arrows. So the fetch length in Lake Superior is much greater than the same wind blowing in Lake Michigan. So we're going to focus now on Lake Michigan. You ready? This is pretty exciting. We still have the defibrillators there. Yeah, okay. Okay, this is Holland, Michigan. Okay, the wind is blowing from west to east, and it's making some little tiny waves that are very pleasant looking, right? This is a nor'easter blowing the entire length of Lake Michigan. How big do you think the waves get? Oh, come on, give me a number. 12 feet. Thank you. How many? What was that thing? Name that price. What was that? Price is right. Yeah. Little lower, little lower. Okay. The answer is they get 25-foot waves in this theoretical model, but I've seen these waves. Yeah, look at these waves. This is breaking waves in Lake Michigan. I've seen 10-foot waves, and I went to, again, Northwestern University on the lake there, and we'd see 10-foot waves in the winter as the winds come blowing down the entire length. So that's the importance of fetch length, blowing the entire length of Lake Michigan with a strong wind speed and long duration. You can get 25-foot waves. That's like Hawaiian size, right? And here's an example of these giant waves. Okay, how do we describe waves? Thank you for appreciating the humor. There's the Princess Diana. Right. All right, there's a guy, as a surfer, we've been describing waves forever, but there's a guy named Galvin who actually quantified the types of waves, and he defined, and this is all empirically based where they have equations to calculate it and so forth, but he defined spilling breakers, which kind of dribble down the face, plunging breakers like the Bonsai Pipeline, a big tubular form, and then surging breakers are the ones that just kind of rush right up onto a jetty or onto a rock ledge, and they don't even break. They kind of go whoosh. You know, you've all seen that, right? Okay, so he defined 3 types of breakers: spilling, plunging, and surging breakers. And here's his diagram here. So those are types of breaking waves. Okay, let's review parts of a wave. We have a wave trough, a wave crest. The wavelength is from crest to crest or from trough to trough. The wave height is the trough to the crest height. If you know anything about surfing, there's a big argument in surfing how to judge wave height. The Hawaiians, for some reason, decided that they would look at the back of waves, not the front of waves. You surf on the front side, but they would, and the back of the wave is usually much less. So I would see a 6-foot wave based on the front, and they'd say, oh, that's a 2-foot wave. So yeah, it's a big argument in the surfing world, but just to let you know, one exists. So wave period is the number of seconds it takes from one crest to go to the position of the other crest. And wave frequency is basically 1 over the wave period, number of wave crests passing a point in each period of time. Okay, as we mentioned, the water motion on a wave is circular and it diminishes with depth. All right, what else? Okay, now as a wave, this is a horrible diagram, and I'll show you a better one. I'm stealing these off the internet, so I apologize. But this is not what waves look like when they come in. Anyway, but I'll show you in a minute. So here's some waves coming in and then finally breaking on the shore. So here's that diminishing circular path with depth. Okay, at this point, basically, there's no wave motion on the bottom. So if you dove down this deep, which might be 20 feet, you wouldn't feel the wave above you at all. What type of sediment would you find down there? There's nothing to carry it there. So typically you'd actually find mud, because the mud might fall from suspension, but there's no currents down there to bring the sand down. All right. So as we go offshore of beaches, so if you swim off of Huntington Beach and dive down 30 feet, the bottom will be kind of muddy. It gets progressively muddier as you go offshore. Okay, now the interesting thing is this wave is coming towards shore, and it's actually, after a while, the bottom of the wave is going to, it's sort of a unfortunate word. It says the waves feel bottom. Sounds like a, sexist thing. But what happens is the waves start interacting with the bottom here. And what happens is the waves start to drag and they go slower because they're dragging on the bottom. All right. And that's what they're showing here. So we go from deep water waves, which are very much sinusoidal shapes. And eventually, so it starts dragging on the bottom and eventually it drags so much, it can't stand as a wave anymore and it breaks. So the reason waves break is from the drag of the wave on the sea bottom. And I'll show you that. Okay, and again, if the sand grains are moved by wave currents, what happens when there is no wave currents? What happens in deeper water? We get mud, right? Okay, so here's waves on beaches. Here's the particle motion associated with the waves. As it hits the bottom and feels the bottom, you can see it starts to drag on the bottom. Eventually it drags so much it just falls forward, and that's why a wave breaks. We all good with that? Okay, remember this diagram I showed you previously shows all the bed forms that were formed associated with flow in a river, a unidirectional flow. What would happen if you looked underneath? So if we go back, what's happening? This sand is being moved by the wave currents. What types of bed forms might we see beneath the waves? This is a paper, this paper won the best paper award back in 1970 or something like that. And it shows how the sandy bed forms form beneath waves. By the way, this is really what happens to waves. In deeper water, waves have a sinusoidal shape, you know, like a sine function. As they start to interfere with the bottom, then they get big troughs, big flat troughs and sharp peaks, crests. So what happens is the shape of the wave changes, and eventually, because of the wave drag, the waves break, they break, and then they rush up on shore. All right. So underneath these waves, by the way, he's got arrows showing the flow is not actually back and forth. It's a little bit asymmetric. So it's pushing water towards shore, pushing water pretty strongly towards shore, pushing water really strongly, and then pushing water back out. So as the wave breaks and runs up on the beach, what happens to the water? Well, some of it percolates into the sand, but a lot of it rushes back out. All right. And that's going to cause problems. All right. So anyway, we have this same diagram from nove movement to ripples to dunes to plain bed. Here's the ripples, here's the dunes, here's the plain bed. It's the same thing that occurs underneath waves. And then in the other direction, it speeds up as the waves go from the interplanar to the inner rough. So it's the same thing happens as the water gets drawn back into the next wave. Okay, so there's this pattern of the waves marching forward till they break and they rush up on the shore, and then they suck back into the next wave. And that's what forms these different bed forms. So anyway, the interesting thing is that we can see these different features on the sand bottom if you dive underward. And here would be this interplanar zone. This is the place, the swash zone that you'd walk on. And then, as I said, as you walk out on these beaches, all of a sudden you fall into a hole. We've all done that. That's going into what's called this inner rough zone. And those are the sand dunes. And the sand dunes are there because the flow is back towards the breaking water, the breaking waves. All right, types of beaches. This is a barred beach. So the waves are breaking here and then they reform and then they rush up on shore here. So that's called a barred beach. Here's a bar at low tide, and that's the wave bar, and this is called a longitudinal trough. Okay, a barrier island is an offshore sandbar, but it's so stable that you can build houses on it. So in Carolina, who is the Carolina lady? You, okay. You were probably on a barrier island, and you have waves breaking out here. This is a lagoonal area behind it. And, you know, you have roads and houses. These areas, of course, are also very low topographically, and they tend to get washed over by things like hurricanes. And they're a big source of problem when sea level rises from global warming. So here's some barrier islands off of, where's Greenville? Virginia? North Carolina. Okay. Okay, so Nags Head, is that where you were? All right, so this is all part of this gigantic barrier island going down here, and that's what it looks like in the satellite image. So this is all shallow water lagoon here. The waves are breaking and rushing up on this barrier island. You can also see how this would be very prone to hurricane disasters because they're very low topographic areas and the water could rush up from the hurricanes. And here's a blow up of this one little area here. All right, so we've defined 3 types of beaches. We can talk about non-barred beaches, barred beaches, which have those offshore bars, and then we can also talk about barrier islands, which are actually larger features. Okay, what type of beach is this? Is this a barred beach, a non-barred beach, or a barrier island? This is Huntington Beach. What? Okay, here a wave is breaking, it's reforming, and then it's breaking again. Barred beach. So this is it's a Huntington Beach. In this case right here is a barred beach. Whereas if you go to Carlsbad Beach, it's breaking right on the sand. So it's a non-barred beach. And then if you go to this place where there's a city built on the beach, that would be a barrier island.
Change?
What's that?
Can they change? Can a
Yes.
barred beach change to a
Yes.
non-barred beach
Yes.
and vice versa?
Yeah, barred beaches can be temporary. Good point. All right, currents on beaches. The famous rip current problem. So what the problem is with rip currents is that the purpose of a wave is to break and push water onto the shore. Some of the water percolates into the sand, but a lot of it rushes back. So you have a problem here. It's like a supply chain problem where you've got water flowing in and water flowing out. So what happens typically is you get what are called circulation cells where the water says, okay, I will flow laterally and then I'll go out in these rip current cells. All right. So the waves push the water in, the water flows along the shore and these longshore currents and then flows out as a rip current. All right. So it's a way, it's a natural way that the beach reacts to the effect of water rushing up on its shore from the waves. All right. So that's an example of a rip current and the issue about swimming in them. And we'll talk about that in a minute. So here's the problem. You go to the beach and you see this beautiful beach and you say, oh, there's waves breaking here. There's waves breaking here. But hey, there's no waves breaking here. I'll go swimming there. Or I'll go swimming here. You don't realize that the reason that there's no waves breaking there is the water's deeper and the current will take you out to sea because it's a rip current channel. All right. So here's another example. Here's the waves breaking here, waves breaking here. You're on the beach. You go, oh, I'll just swim here. There's no waves there. And then you swim out here. It's deeper water. And the current is taking you out because that's what rip currents do. Let's go back up here. So the rip current wants to take you back out. And so what everyone does is say, well, I'll just swim back to shore, but I don't want to swim where the waves are. I'll just swim in this channel. And of course, then they get tired and they get swept out to sea and so forth. Ironically, if you'd gone over into where the waves are breaking, that's where the current is towards the shore. So even if you didn't even swim, the waves would push you back to shore. Does that make sense? So these are big circulation cells and the rip channels are taking you out to sea and the waves are pushing you back onto land, onto the beach. Rip currents have all sorts of interesting characteristics. Here's a bunch of spaced rip currents. So there's rip current here, a rip current there, a rip current there, a rip current there, rip current there, and a rip current there. There's a whole bunch of theories about these, but I won't tell you about them. I could, but well, maybe I will. Okay, at low tide, here's what a rip channel looks like at low tide. So tides now drop so you can actually see the offshore sandbar and the rip current. Here's an example of a rip channel being exposed right as the tide is dropping. Here's that longshore trough where the water circulates around. Okay, so that was enough on rip currents. Our next topic is wave diffraction and refraction. So diffraction is when waves are coming, here's the waves coming here, and they hit a hole like in a jetty or something. And this is what happens to the waves as they go through that hole. All right. And so the waves become very weak in that direction as they fan out, and they're strongest, if they go straight in. Okay, so that's diffraction through a hole. And by the way, I have a theory, all those cargo ships offshore, I think they're probably causing diffraction of the waves that are coming in, but that's another theory I'm working on. All right, so wave refraction is when the waves bend because the water depth changes. So if you have a headland here that's shallower water, the waves will actually bend as they go around this headland. Now, I don't know if you remember, but waves, maybe I didn't mention this, waves in shallow water move slower than waves in deep water because the waves in shallow water are dragging. So they're dragging, so they can't go as fast. If you're in deep water, the wave can just move without any problems at all. Okay, so here's some waves coming in, and the bottom is a little bit shallower here, and they're moving slower here and faster here, so the waves are bending. See that? Okay. So that's called wave refraction, and it's significant, as we will talk about in a sec. But we all got diffraction, refraction, got it? All right.
Dave, while you have a break, I have a question here for you.
Okay.
Why do you not hear about rip currents all the time, or are they always there?
They are, okay, the question is why do we not hear about rip currents all the time, or are they always there? Probably it's social, in part, if nobody's going to the beach, then nobody cares. So probably in the winter, we talk about them less. And secondly, it's dependent on wave height. So the strongest rip currents are associated with the largest waves, as you might guess. So the more water that's coming in, the more water that's going out. So when the waves get really big, then your rip currents get really strong. So those are the issues. Okay, here's examples of wave diffraction through a hole. And here's an example of wave refraction around a point. We're going to get some better stuff though in a sec. Okay, here's some examples of wave refraction in real life. So here's some waves that are breaking on a headland, and you can see the deep water wave. You can see the wave bending. See how it's coming in like there? It's really well shown here. Look at, here's the deep water wave, and it's curving way over here. See that? So those are all, that's an example of wave refraction as it goes along this headland. You see, oh, look at that. See that? Everyone sees that? All right. So that's wave refraction. Why do we care? Good question. I don't care. Okay. Wave refraction. Waves feel bottom and slow down. So we got the bending. What happens is when you have the waves coming in obliquely, it causes a current. And the name of that current is, nope. It's when they come in, all right. Longshore currents. The consequent of wave refraction is longshore currents. So what happens is the waves kind of come in and they kind of start pushing the water along the beach. So bending of waves as they approach the coastline. Part of the waves is in the shallow area, slows. Part of the waves in deeper, continues with higher speeds. This results in a longshore current. So here's an example. Here's the waves bending. Here's the longshore current, and this is pushing you. Now, the real scary thing at Huntington Beach is not so much the rip currents, it's the longshore currents. When the waves get big at Huntington Beach, you can have a longshore current that is as strong as a river. So what happens, people will swim out, not realizing that they're in this condition with a longshore current, and they'll drift down the beach half a mile in like an hour. It's that strong. So now, fortunately, it doesn't suck you out to sea or anything like that, but it can certainly help you lose your car. And if you try to paddle against it, it's very difficult. So anyway, that's the longshore current resulting from wave refraction. Okay, and here's the waves coming in here at an angle, and here's this longshore current that's formed as a result. All right, other things that waves can do. Backwash. So when a wave rushes up on the shore, it can actually be reflected back and form what's called a backwash or a reflected wave. Now, when it's a little tiny wave, it's nothing to talk about, but in some cases, it can be enormous. So this is a wave slamming up against some sort of seawall, and that must be going up 40 feet or so, and it's going to form a wave that goes back out into the sea. All right, here, and it also makes some spectacularly beautiful images as shown here. So we have a backwash here. Here you can see some guys caught in the wave being thrown in the air. Okay, this is an example. I was walking down Newport Beach a couple of months ago, and part of the beach was very steep. See how steep that is right there? And it was much flatter here. See how it's flat here? Well, here the waves would run up and they'd slide back down, and here's the backwash or the reflected wave coming back. So down here where I am taking this picture, there's no reflected wave because the shoreline's not steep enough to cause the reflection. Whereas on the steeper part of the beach, we have this reflected wave and going back as backwash. All right, so this again, it's not very dramatic because it was only, this high, but this demonstrates how a steeper beach would tend to form better reflecting waves or backwash than a flatter beach. And again, beautiful backwash examples.
Another question, Dave.
Yep.
I've stood on the beach many times and seen waves coming from two directions. Is that just a function of the directions from which the waves were generated? That hundreds or thousands of miles away?
What
dumbfounded
beach?
you.
Is this you or someone else?
No, this is me. I think I know
What?
the answer to this, but I want to see what you say.
Well, what beach? What beach?
Oh, many beaches. I've been,
Two different
Like
directions.
two different directions. Yeah. Some of it's refraction, I think, and the other, maybe there's a dominant one, but they both look the same. They come in at the same troughs, and the same crests from two different directions. I think it might be a wraparound function possibly of the refraction that comes around a point.
I'm a surfer and I surf in fact, I would have been surfing today if it wasn't for this class.
Oh, thank you.
I don't, I know a lot about, what I'm saying is I know a lot about waves, but different swell directions.
Yeah.
I'm not, I mean, like if you're near a jetty, sometimes the waves will bounce off the jetty, like the Wedge and
Yeah.
other jetties.
I suspect that's a lot of it, but also if you get, two storm centers that are off.
No,
they
that's
come in
called, in the terms, that's called a combo swell.
combo swell.
Yeah, and but I've been in combo swells before, and I don't really see that dramatic of a change. So unless you show me a picture of it, it's
Yeah.
harder for me to explain it.
Yeah. Okay.
Was there another question?
No, a comment.
Okay.
I grew up on Lake Michigan.
Oh, there you go. Which,
When wind changed radically, you would see two different types of waves coming one way or the other.
okay. Yeah, I could see that.
Especially if it's coming from the northwest. And now it's coming from the southwest.
So which Michigan, where'd you live?
Straight across from Milwaukee, a place called Muskegon
In Michigan.
in Michigan.
Oh, so near Holland, a little north of Holland.
Just north of Holland.
Oh, okay.
And surfed with Lake Michigan, but only during the storm.
Lake Michigan is where I've seen this happen. That's one of the places.
No, I definitely, if you have changes in wind direction in a small fetch area, you could see something like that very dramatically.
Be radical.
No.
The southerly wind. Yeah. Just have cold water. But if it changes from north to south quickly, you'll see waves coming two different directions.
I could, in that situation, I could see that, yeah. But in terms of Huntington Beach, Newport Beach, Dana Point, I don't see much evidence of that. It's usually one dominant swell, even if it's a supposed combo swell. Yep, Susan.
What about seasonal waves, like in the North Shore of Hawaii? They always come around November and December, but the rest of the time it's totally calm. So what causes that kind of wave only to appear on those 2 months a year?
Wait, let me repeat your question. The question is, why does wave size change seasonally? And the answer is, on Hawaii, all of those storms are up in Alaska. So unless you're in the winter, when you have giant winter storms coming through, there won't be any waves. Same for Nazaré in Portugal. It's usually largest in the fall when they have big North Sea storms. But the rest of the time at Nazaré, there's no waves at all, you know, like 1 foot waves. And then there's some gigantic North Sea storm 1,000 miles away with 100-mile-an-hour winds, and you get 100-foot waves. So it's all related to the storms. So there's a website called surfline.com, and they give you predictions of wave heights that are used for all the surfing competitions. And they study the storm centers, and they do these calculation of wave height and fetch and all those sort of things. And they will predict when that swell will arrive at your beach. And that's part of their service.
Okay. So in Hawaii, it's because of the storm.
Yeah, and then on the south, they also get storms on the southern side during the summer season coming from the South Pole area. So southern hemisphere, I mean. But it's all associated with storms. Big storms equal usually big waves, though further away. All righty, any other questions? Yep.
I live in San Clemente,
Yeah.
and they say that
Thank you. In San Clemente, they say that they have to import sand. So I was just wondering what causes that?
I don't know specifically the San Clemente case.
Well, trestles. It would be near trestles.
Huh. There's a whole sand budget. Sand comes in from the rivers. So the question is sand replenishment projects that are occurring at San Clemente. There's a sand budget. And so if you affect the sand budget, that means if less sand is coming in on the rivers, then your beach would tend to just decay with time because it gets washed offshore or washed down the coast. So one issue is the amount of sand coming in still significant? Another problem is, of course, sea levels rising from the global climate change. And as sea level rises, that also tends to erode the shoreline. So a lot of people think everything's associated with global climate change. It turns out there's a third factor, is a lot of these areas are subsiding. So if the land is subsiding, that also has the effect of being the same thing as sea level rising. So if I just said, you can't really tell the difference between sea level rising and land subsiding, you have to analyze them as two different functions. So land subsidence, so a lot of the stuff that they're saying in Mississippi is due to global climate change is also because of land subsidence, because you're in a delta and the delta compacts with time and then it sinks into the mud. So it's a complex problem. So I don't know the example in San Clemente, but it's probably associated with the source of sediment, sea level rise, and or subsidence. Sorry, I didn't have a clear answer. Okay, changes in beaches over time. Here's a sort of an additional point. Why do you think a beach would change from summer to winter? So beaches change. So here's a winter profile and a summer profile. Why do you think there's a winter profile and a summer profile, say in California?
The water action. I mean, there's storms different times of the year.
Right?
The storms affect the wave action, which affects what happens on the beach.
Right. So the idea is that the storms are very different in the winter than they are in the summer. So we have our most intense storms in the winter. If you put a lot of energy into a beach, if you put a whole bunch of energy into this beach, it can erode away the sand. All right. In the summer, when the waves are calmer and more gentle, it can push that sand back up. So what happens is if the waves get larger, it changes the whole beach profile because the energy is much greater. So if the waves are bigger, that means it can move sand further into the water, right, at deeper water depths. So this whole profile changes during the winter. And then in the summer, when the waves are gentler, it tends to push the sand back up on shore. So in the winter, if you see these little cliffs along the beach, this is from shore erosion associated with the waves changing from being more gentle in the summer to being more intense in the winter. All right, something I'm sure we've all seen and maybe you've thought about. Okay, examples of waves. All right, the first thing I'm going to do, these things are called wave ripples. This is more about ripples than waves, and I'll see if this works. And we'll probably have to watch an ad.
When you need internet, but your family interrupts you with streaming, video games, online classes.
Hey, I've just bought Google Prime on this. I'm kidding. Okay. So what they did here is they, this is showing, these are waves in a flume. And what they're going to do is they're going to change the wave character and they're going to make ripples. So wave action drives sand transport. These are called wave ripples. They're called symmetric ripples because they move sand both equally in either direction. See that? And they've sped this up so we can see it in a shorter period of time. It's even got a soundtrack. I can actually speed this up. Oh, impatient? Yeah, there we go. Using time lapse. Here we go. All right, so those are ripples forming associated with waves in the flume tank. If you're a sedimentologist, you'd be just drooling with anticipation of this. Okay, so now they're going to shorten the wave period. They're going to increase the wave frequency or shorten the period. And you can see the ripples became closer together. See that? So the ripple spacing here is a function of the frequency of the waves. Now they're going to slow that down. And now you can see that it'll widen the spacing of the ripples. Isn't that fascinating? People are getting paid to play with sand like this. All right, I think that's about good. Now all I have to do is find my presentation again. All right. Okay, big waves at Corona del Mar and the Wedge. So this is all sort of, I'm a surfer, remember. I have a picture of a surfer on me. And now we're going to sort of entertain you with things. You've all been to big Corona del Mar beach, right? So a few times a year, there's an enormous south swell and they get gigantic waves there. So picture in your mind what big Corona Beach looks like. We know where it is. It's right here. Well, this is what it looks like when there's giant waves. So there are waves breaking inside this is the inlet into the harbor. So that's a guy standing up. So that's about a 10-foot wave. Come on, that's pretty impressive, isn't it? All right. Now there's a famous surfing spot that's also an interesting wave from sedimentological purposes. And it's called the Wedge. We all know the Newport Wedge. Have you all been there? It's kind of it's a hassle to get to. And what happens there is the first wave comes in, bounces off the jetty. Here it's reflecting here, hits the second wave. The waves combine in height and get enormous. Okay, that's how the wedge forms. Here's an example of that combined wave. And it's breaking in about 5 feet of water about 100 feet offshore. It's an amazing thing when it gets this big. So let's see what we got here. I got some entertainment here. Oh no. Uh-oh. Well, that wasn't good. Dune migration. All right, Dave has to be creative here. Oh God. There we go. Control C. Oh, come on. Oh, Mr. Wizard. Okay, I'll try another way. Control C. There. Why isn't it opening? Is there another screen here? Oh, is it over here? No, actually, I can put my mouse over here. No, I know. What I'm saying is it might be hiding the screen. Okay, here we go. There. All right. So this is big waves at Corona del Mar, and I'll speed it up to see. There we go. So these are big waves coming in at Big Corona del Mar. And so the boats have to come in and they have to deal with these large waves that are breaking. Look at all the surfers out riding. So again, a few times a year, you get giant
We're not
waves.
able to see the video remotely.
Any thought on that? All right. Well, we're getting to the limits of my, can you guys online see this PowerPoint? Let's see if they can see that.
We see the PowerPoint.
All right. Unfortunately, no, I did that. Yeah. No, for some reason, it's not getting it. Move here. Do we have any helpers online?
Lucy, do you have any ideas about that?
Hi, sorry. You can try, did you copy paste the link and put it on the Internet Explorer page?
Yes, but nobody can see it online.
Get out of share screen and then redo it again.
Get out of share
Are we
screen.
messing with
I'm
a
not in
place we
share
probably
screen.
don't want to go because we might lose everything?
No, it's from his side, from where he's doing it.
Okay.
Urgh. So get out of shared screen.
So stop share screen and then restart it up again.
I'm not in shared screen right now. What's shared screen? Do you know what that means, Gary?
Yeah. You have to be in the Zoom. You have to be in the Zoom. Zoom one.
Oh.
So the video isn't playing.
Video is not playing, right? I think we're gonna.
Why?
Is this the video? Oh, no.
No. It was in the PowerPoint.
Oh, it's in the PowerPoint. Just
It's
copy.
the second one, not the first one, the second one. You missed an HT. That's all right. It's all right. This is the end of the presentation for today. Yeah, that's what I thought. It got stuck over there.
What's the video called? Maybe I can just search it up.
No,
Oh, it's a specific.
that's what it's called. Isn't this exciting,
Thanks,
everybody?
Lucy.
Control V.
Why isn't it? Oh, there you go. No, I already did this one.
Oh,
Sorry.
so it's the third one?
I guess the third one, yeah.
Okay. Is it Control C, and then Control V? Oh, okay.
Good God, somebody's calling me.
Is it this one?
Yeah, I hope. Okay, this is the wedge. Sorry, I gotta turn this off. I was the only guy not to turn off their phone. There it goes. There's always one. All right. Can you hit the forward? Here we go. Anyway, this is the wedge, just to tell you, the waves, again, bounce off that jetty and you get enormous waves that show up. And these guys are completely and utterly insane. Now, watch this one. They're taking this is the reflected wave. It's a little tiny wave. And then boink, they hit a backwash in that case, right? He hits a backwash and he goes up 20 feet or 30 feet.
Yeah, maybe I should.
All right, and then there's a guy. Doesn't that look like fun? Yeah. Now, if you guys heard, I think it's this video. Did you hear about the jet ski incident a few years ago? Well, I think it's in this video. Look at this guy's going right into the tube and then kerdunk. All right, let me see. So we got this going.
My vision is pretty good. Oh my God.
All right. Oh, here it is.
I know, it's kind of surprising. Like,
Okay, here we go. Here's the jet ski incident. So this guy, okay, here we go.
I couldn't see shit on my face. Also, I can see.
By the way, hey, we can hear you
Oh my God,
online.
I cannot.
Can you tell her to stop? Okay, so anyway, there's this guy on a jet ski. He's obviously a tourist and he doesn't know what he's doing. And he sees this big wave and he goes, I'll just go into the harbor, into the jetty, but there's no hole through the jetty. So he sits there and he just loses his jetty. And a second later, you can see there's two people swimming. That's the lifeguard getting him. And there's the jet ski up in the rocks. And there's a couple of heads that are bobbing. I don't know why that went there. Anyway, so this is the excitement associated with the Newport wedge. Apparently, they lived through that incident, and they were saved by the lifeguards. But that just gives you an idea of how nasty it can get at the Newport wedge. Let's see what else we got here. This is all sort of fun things. We're running a little on time, so let's go to the giant waves. This is probably Nazare. And I'll put it here. And I go there. And I'm hoping there's a good ad for you guys. All right, skip ad. Okay, this is supposedly an 80-foot wave that he's going to ride. This is in Nazare. So that's the jet ski that pulls him in. And here he is riding the wave. And that's a lousy picture. But enormous waves. So let's see if we can see that again. So here's the jet ski pulling him in. Here's the guy riding the wave. Look at the size of that wave. Supposedly an 80-foot wave. One of the ironic things about these giant waves is they're so large that nobody knows how to measure them. They actually take cutouts of the guy and they say, oh, he's about 5 feet tall, and they try to do it by hand. You'd think if we could get a spacecraft to Mars, we'd be able to accurately measure the height of waves, but apparently not. So this was the Guinness World Record for the biggest wave ever surfed at the time. All right, let's see if I have any other choice things here. There's one more here. Oh, I think I'll go to the next slide. And then there's this one. I don't know what this is, but it must be good. Oh, this one. This is fantastic. Have you seen this one, Frank?
On 60 Minutes.
Look at it. So this gigantic slab of ice falls into the water. What's a man to do or a person to do? Forming a gigantic wave. What's a person to do? It's freezing cold water. Yet, there they are. So he's still being towed by the jet ski. I think that's a wetsuit for sure. With a t-shirt. I think that's a rash guard on top of it. So now he's let go of the tow rope and he's riding a wave from the collapse of that glacier. And the wave is probably what, 7 feet high? Something like that. So how entertaining is that? All right, and look at that. What scenery. Okay, that's the end of today's class. If you guys have any questions, I will gladly waffle.
Anybody? We don't have any on the Zoom connection, so if there's none here, I guess we can let you go.
Okay, I hope you enjoyed the class. Thank you.